Hey guys. Alright, so today we're going to do a couple of practice problems on calorimetry. And so I told y'all we were going to do some little practice board work. Since I am not here today, you are going to get to watch a video. And so let's go ahead and get started. We've got a couple of problems to work. Now remember, when we talk about calorimeters, we use those coffee cup calorimeters and they work great. But we're going to use the equation Q is equal to C delta T. And so remember, your Q is your joules. Now Q is different from delta H. So whenever I talk about Q, this is your joules of energy. So if I have a negative joules, that means I got colder. I dropped in energy. If I have a positive Q, that means I got hotter. So it's kind of the opposite of delta H. All right, you'll measure mass. We like to have this right here in grams. So I'll put joules in grams. Okay, this is your specific heat. So specific heat is usually going to be joules per gram degrees Celsius. And then delta T is going to be your change in temperature. So I can either do Celsius or I could do Kelvin. It just kind of depends. They're both based off of the same scale. So if I go up a degree Celsius, you go up a degree Kelvin. Now, when we do this, you do your last minus your first temperature. So final minus initial, or last minus first. All right, so let's look at question number 1. It says, how much energy? That is what you were looking for. How much energy? If you do not have a calculator out at this point, go ahead and get one out. That should be one of the first things that you always pull out. All right, so how much energy is needed to change the temperature of 50 grams of water by 15 degrees Celsius? So I am looking for this Q value. So that is my variable I am searching for. And I want to change the temperature of 50 grams of water. So that would be my mass. So 50 grams. We know the specific heat of water. It is 4.184. And my temperature change. Well, look, it didn't tell me a first and a last temperature. It just says, hey, I changed it by 15 degrees. It didn't say I got hotter or I got colder. If it said I got colder, I would put this as a negative value. It says I changed it by 15 degrees. So just put 15 right here. And now I can just multiply all three of those across. So I would say, let it start up. All right, 50 times 4.184 times 15. And this right here would be my total value. However, if I go back and look at my problem, this has 3 sig figs, 3 sig figs. I want my answer, instead of it being 38 joules, I want to round that to 3 sig figs. So 1, 2, 3. There's no decimal, so I would count to the left. What is that 8 going to make the 3 do? Right, it's going to make it round up. So 3, 1, 4, and I still have to put a 0 in for this placeholder because 314 is a lot different than 3,140. So this right here would be my answer. All right, that was easy peasy, wasn't it? Okay, let's look at number 2. It tells me how many grams of water can be heated from this temperature to this temperature, and it tells me the joules. All right, so I know to use MCAT, even though it's not telling me that I'm using a calorimeter. I know, well, look, here's the temperature change, here's joules, I'm looking for grams. I plug it into MCAT. So Q is equal to MC delta T. All right, so it tells me how many joules. And remember, I need it to be in joules. And so I have 12,500 joules is equal to, well, I'm looking for my mass. So that is my X. My mass is my X. I could have left that as an IL. Sometimes I do. 4.184 is the specific heat of water. And then your temperature changed. It started off at 20 and it heated up to 75. So last minus first. 75 minus 20 would be 55. And now I want to plug this right here into my calculator. And so I'm solving for X. That means I need to multiply these two numbers together and then move them to this other side. And some of y'all, instead of doing it step by step by step, some of y'all like to put it all into the calculator at one time, which is fine. So my mass would equal to 12,500 divided by, you've got to put both of these two in a set of parentheses because I have to multiply these before they get moved to this other side. So I would say, parentheses, 4.184 times 55, close parentheses. So I'm going to come over here to my calculator. 12,500 divided by, parentheses, 4.184 times 55, close parentheses. That way it does that order of operations. It does this multiplication before it allows it to divide. So my answer is 54.319. All right. So if that is the case, I need to do 3 sig figs, 2 sig figs, and then 1, 2, 3, 4, 5, 6 sig figs. So I want to round my answer to 2 sig figs. So 1, 2. What would my answer be? It would be 54. And then since I'm talking about mass, my units, because we don't like naked numbers, we're going to put a unit on it. It'd be 54 grams. All right. So moving on, let's look at number 3. What is the final temperature after 840 joules is absorbed by 10 grams of water at this temperature? All right. So this was my beginning temperature. Here is my mass. Here is my Q value. I'm looking for my final temperature. So let's plug this in. So my Q is your 840 is equal to, okay, my mass is 10 grams. Specific heat of water is going to be 4.184. And then look, last minus first. Well, I'm looking for my final temperature. So I'm going to do X minus 25. So we're going to have to do a little bit of math right here. We're going to have to end up foiling stuff out here in just 1 second. So I want to go ahead and simplify this by multiplying this together. So that would be 840 is equal to 41.84 X minus 25. Now, I'm going to take this and FOIL it. So it'd be 840 is equal to 41.84x minus, well, what is that number? 41.84 times 25. And that would give me an answer of 1046 once I FOIL it. Now I can finish simplifying, and it's just like your algebra problems. I want to get x by itself, so I'm going to add 1046 to both sides. That way they cancel out. And so 41.84x is equal to, what is that number? Plus 840. That would be 1886. All right, so I want to get x by itself. So divide by 41.84. Divide by 41.84. All right, so take your answer and divide it by 41.84. So it tells me, remember, we were solving for the final temperature. What did it heat up to? What was the last temperature? And so we said it was 45.076. Now, does that make sense? Did it heat up? Well, if I'm absorbing energy, it should heat up. So since this number is higher than the initial temperature, that does make sense. So if I look, there's 2 sig figs, 3 sig figs, 3 sig figs. My smallest amount of sig figs is 2. So I want to do 1, 2. So my answer would actually be 45 degrees Celsius. And that would be my final temperature. All right. Now, if I look at the next problem, Now I'm going to heat up a little piece of metal. I'm going to heat up a piece of aluminum. And guys, I want to see what happens. I'm not putting it in water. But if I look at this, I want to know my energy. I want to know my Q value. All right, my mass is 8.50 times 10 to the second. Hey, remember, that right there would be the same thing as writing just 850. They just wanted to write it in scientific notation. We'll go ahead and keep it that way. That way we don't get confused. So this would be 8.50 e to the second. But that really is the same thing as 850 grams. All right. I don't know my specific heat just yet. I do know my temperature change. It went from here to here, so last minus first. But look, I know, oh wait, there's my specific heat, the heat capacity, the specific heat, joules per gram degrees Celsius. That tells you the specific heat of aluminum is going to be 0.9. And now I can do the last minus first. And so your final temperature was 94.6 minus the initial temperature of 22.8 gives you a total temperature change of 71.8. It got hotter. So my Q value should be a positive number here in just one moment. So 71.8. That's what I'm saying. It's kind of like the opposite of delta H, because with delta H, if it's getting hotter like an exothermic reaction, that delta H value would be negative. This is where it's different because Q is not the same as delta H. All right, so I can multiply all three of these numbers together to find out how much energy that piece of aluminum absorbed. So I'm going to put 8.50 second comma 2 times 0.9 times 71.8. And so my Q value is going to be equal to 54,927 joules. Now, going back, I don't worry about constants, and this aluminum will always be that for the specific heat. So I don't worry about constants when it comes to sig figs. Now, if I look, that has 3 sig figs, 3 sig figs, 3 sig figs, so I want 3 sig figs. 1, 2, 3. What is the 2 going to make the 9 do? Nothing. Good, nothing. So 5, 4, 9, and I'm going to add a 0 and a 0 for your placeholders. Now, double check it. There's no decimal, so I count in this direction. So it'd be 1, 2, 3. That would be your 3 sig figs. Now, don't forget to put that unit, otherwise it is a naked number. All right, on number 5. Okay, on number 5, I'm taking a piece of metal that has this mass. So I'm going to use 2 different colors right quick. So I've got a piece of metal that is this mass that was heated up to 100 degrees Celsius. Kind of like last year when we took that piece of metal and we heated it up, and then we put it into some cold water. So you want to take this heat, not the room temperature that it started off with. We want to heat it up to this. All right, and so then we put it in 100 mils of water. So guys, here is my information starting with my water. I've got 100 mils of water that was originally at this temperature. The metal and the water are allowed to come to an equilibrium. That means as you put that piece of metal in, the metal's going to cool off while the water warms up, and eventually they're going to come to some type of equilibrium temperature, which is right here. So this is not only the temperature for the water, but it's also going to be the final temperature for the piece of metal. So assuming that no heat was lost to the environment, calculate the specific heat of the metal. So in a case like this, where I'm putting something into water like this, I'm going to have to use MCAT 2 times. Because if I can figure out how much energy the water gained, that should be equal to how much energy that the metal lost. The only difference here, that number will be the same, but I need to worry about the positive and negative signs. Since I am losing energy, I would put a negative sign beside it. All right, so the first thing that we can do, the only thing I have all of my info for, is the water. I'm going to have to solve for how much energy the water gained, and that will be the same Q value for how much energy the metal lost. And then I can actually solve for the specific heat of the metal, because I don't even know what this metal is. I couldn't go look it up if I wanted to. So let's figure out how much energy the water gained. So because of density, remember, density is equal to mass divided by volume. And we know the density of water is 1. So if the density of water is 1 and I have 100 milliliters, how many grams would that have to be? How many grams would that have to be for me to have a density of 1? Well, it'd have to be 100 grams. So 100 divided by 100 would give me 1. And so I know that this is equal to 100 grams of water. And we know the specific heat of water is 4.184, which is kind of coincidental that the number of joules in a calorie is also 4.184, because everything was based off of water back in the day when they came up with this. And then I want to do my temperature change. So look, the water was initially at this temperature. When that hot piece of metal was put in, it went up to this temperature. So I'm going to do last minus first. So that would be 27.8 minus 23.7. And that would give you a temperature change of 4.1. So this right here would be a temperature change of 4.1. So now I can multiply all three of these together to figure out how much energy the water gains. So I would say 100 times 4.184 times 4.1. So that means the water gained 1,713.8 joules. So that energy had to come from somewhere. It actually came from the metal cooling off. And so if this is how much energy the water gained, that's also the same amount of energy that the metal lost. I'm just going to put a negative sign on it. So I'm going to go ahead and write that right here. So the energy that the metal lost is going to be negative 1,713.8 joules. So now I'm going to come over here and I'm going to do my Q values one more time. Now that I know how much energy the piece of metal lost, and I know the mass of the metal, and I know the temperature change of the metal. So now let's come over here, and I like to write, and a lot of teachers do, like to write these right here, Q of your water, Q of your metal. That way you don't get confused. And that way when it comes time for a test or a quiz, I can follow along to see, hey, where did you get this number? What are you doing? I know that you're working on the metal. All right, so you've got a mass of the metal of 59.047. I am looking for the specific heat, which is your X, and now I want to know the temperature change. So like it was really hot, and then when you added it to water, it cooled down to this. So this is your last temperature. So final minus initial. So if I take 27.8 minus 100, that will give me a temperature change. Look, it's a negative value because it decreased in temperature. So negative 72.2. So negative 72.2. All right, so I can, 1713.8. All right, so I want to multiply these two numbers together and then move them over here. So I'm going to say negative 1713.8 divided by 59.047 times negative 72.2. All right, so let's plug that into the calculator. We can say negative 1713.8 divided by, and remember, I want to put this in a set of parentheses, that way order of operations is satisfied. 59.047 times a negative 72.2. So my Q of the metal, sorry, not my Q of the metal, I'm sorry. The specific heat of the metal is going to be 0.401999. All right, so if I look back at my problem, 3 sig fig, 3 sig fig, 5 sig fig, 4 sig fig, 4 sig fig. My smallest number is 3 sig figs. So if I look back over here, because it's going to be like a 9, 9, 9, 1. If I look back at that, I want 3 sig figs. 1, 2, 3. What's that 9 going to make the 1 do? Okay, it's going to make it go up. So this would be 0.402 joules per gram degree Celsius. And that would be the specific heat of a metal. And guys, that's a small specific heat, so that makes sense. Usually metals are going to have a specific heat less than 1. All right, now for the last one. In a coffee cup calorimeter, 100 grams of water and 100 mils of HCl are mixed. The HCl had an initial temperature of 44.6 degrees Celsius, and the water was originally at this degrees Celsius. After the reaction, the temperature of both substances was this temperature. Was it endo or exothermic? Well, guys, look at the reaction. It was originally 44.6. And so for the reaction, not the water itself, but for the reaction, look, it went from 44.6 to 31.3. So it got colder. What do you think happened? Yeah, it's going to be endothermic because it was pulling energy from the surroundings into the actual reaction for it to happen. And remember, you cannot take the temperature of the reaction. You can only take the temperature of the surroundings. So I would say endo, and you'd have to explain and say, since the temperature decreased, and I'm not going to write this, I'm just going to talk about it. Since the temperature decreased, it is showing that the energy from the surroundings was going into the system to make the reaction endothermic. All right. So now I could actually calculate how much heat the water gained. And so I want to know my Q value of the water. Okay, do I know how many grams of water? Yeah, I've got 100 grams. Do I know the specific heat of water? It is 4.184. And my temperature change of the water. Well, look, this is the temperature at equilibrium, whenever they equalized. And this was the original temperature of the water. See how I increased in temperature? All right, so I'm going to say last minus first. So 31.3 minus 24.6. It has a temperature change of 6.7. So 6.7. So I can multiply all three of these together to see how much energy that water actually gained. So I can say 6.7 times 4.184 times 100. And it's going to give me a value of 2,803. So the Q of the water is equal to 2,803.28. And now going back, 4 sig figs, 4 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. I would want 3. 1, 2, 3. And so what is this answer going to end up being? Well, if I put 2800, because that 3 is going to make the 0 stay the same, that's only 2 sig figs. And so to get the 3 that I need to put that right there into scientific notation. Even though there's not a decimal right here, it's not showing a decimal, there is a decimal at the end. So I want to move this decimal to where there is one number in front of it. So 1, 2, 3. So in scientific notation with 3 sig figs, I would have to say 2.80 times 10 to the third power. And since I'm talking about heat, I would put joules. All right, so hopefully that'll help y'all out. Y'all do have a set of questions that y'all are going to work on today. Please make sure that you do put this in y'all's binder. Go ahead, and it's already on the table of contents. So today's date is 10/1 of 2005, and we're going to call this the Calorimetry Boardwork. Y'all have a fantastic day, and I will see y'all on Friday.